We've travelled to lots of weird places on this show, from the interiors of black holes to the time before the Big Bang. But today, I want to take you on a journey that has got to be to the weirdest place in the modern universe, a place where matter exists in states that I bet you've never heard of. Today we take a journey to the centre of the neutron star. Neutron stars are arguably the strangest objects in the universe, if we don't count black holes as actual objects. And honestly, neutron stars are even weirder than black holes in some ways. Now, we've talked about these things before, about how they form from the dead cores of massive stars left over after supernova explosions. We've seen how they look from afar, perfect metronomes of flashing light as these rapidly spinning stars sweep us with their jets as pulsars. And we've explored strange processes that occur as a neutron star approaches becoming a black hole. But what we've never done, at least not properly, is to really explore the insides of these beasts. And it's time we did so, because there we'll find states of matter that exist nowhere else in the universe. For this journey, we're going to need an unthinkably advanced spacecraft. In fact, there is no imaginable technology that could withstand the conditions that we're about to experience, so we're relying on the amazing power of bad science fiction. An indestructium craft to withstand the radiation and pressure, and an anti-gravitational field to resist the ridiculous gravitational forces. And all this stuff is going to come in handy as soon as we approach the neutron star. The first thing we encounter is its magnetosphere. This is the strongest magnetic field in the universe. Even the weakest neutron star fields are 1 billion times stronger than those of the Earth or the Sun. This magnetosphere is very different from the magnetized space around the Earth or the Sun. It's filled with electrons and positrons. These matter-antimatter pairs are created out of the extreme energy photons in the magnetic field. That field then becomes a particle accelerator, with electron currents flowing one way and positron currents flowing the other way due to their opposite electric charges. These and other charged particles end up being blasted out along the poles of the magnetic field, and their motion in those jets results in the radiation that we observe as pulsars. When we're nearly through the magnetosphere, we start to notice that the neutron star's surface is a little fuzzy. We're seeing the star's atmosphere. Similar to the Earth's atmosphere, this layer of haze starts out very tenuous, almost a vacuum, and then gets denser as we drop. But the similarities end there. Earth's atmosphere is mostly oxygen and nitrogen in molecular form. Pressure increases as you go down, so that at Earth's surface, the weight of all that gas on top of your head is about 200 kilograms. But the neutron star's atmosphere is not made of atoms. Rather, it's a plasma, in which atoms have been stripped of their electrons, or ionized, due to the extreme heat, around 1,000,000 Kelvin for a young neutron star. Those nuclei are mostly hydrogen and helium captured from the nearly empty space surrounding the star. And while Earth's atmosphere is something like 100 kilometers thick, depending on how you define the edge of space, the neutron star's atmosphere is barely 1 meter thick, with most of the plasma confined to a thin shell 10 centimeters above the star's surface. Now this is due to the insane gravity at that surface, which I'll come back to. Once we've landed on the surface, our heads are in the vacuum of space, while our feet are in a foggy plasma with a density many million times greater than anything on Earth, and the gravitational pull here is something like 100 billion Gs. Here, we start to encounter the first truly strange states of matter. See, the matter at your feet is not all that different from the stuff of a white dwarf, the dead core of a lower mass star like our Sun. The plasma is crushed so tight that electrons are on the verge of overlapping. But as we saw in previous episodes, particles of the fermion family can't occupy the same quantum state. The matter has become what we call degenerate, and electron degeneracy pressure stops further collapse and ultimately holds the atmosphere up. Having landed on the neutron star, we actually do have a solid surface below our feet. It appears to be some strange sort of crystalline material. Now, that's pretty weird because we normally think of crystals as lattices of atoms connected by electron bonds. but the stuff below our feet is still completely ionized, still stripped of its electrons. In fact, it's a frozen plasma, in which its nuclei are locked together in a regular lattice. You might wonder how nuclei can bind to each other, given that they're all positively charged and so should repel. Well, at these densities, nuclei are pushed so close together that their mutual repulsion actually prevents nuclei from slipping past each other like gridlocked traffic. And the symmetry of that repulsion forces nuclei into a regular grid. In this case, the crystalline matter is mostly iron. That iron was the last element forged in the core of the star in the hours before it went supernova, and some of it still survives here at the neutron star surface. Okay, now the real journey can begin as we start to tunnel into the star's interior. We enter the outer crust of the star. Density only increases as we go down. Suffusing the crystal lattice is a gas of electrons, a so-called degenerate Fermi gas that holds up this part of the star from further collapse. The deeper we go, the more energetic these electrons become, and soon those energies are high enough to drive some very exotic nuclear reactions. Electrons start to be driven into the iron nuclei in a process called electron capture. The negatively charged electrons merge with positively charged protons to produce neutrons. In this way, iron is converted into elements with fewer protons, but which are still just as heavy as iron and very, very neutron rich. Once we've gone down a few hundred meters, we see nuclei that can't even exist outside a neutron star. Where the star is 50 billion times the density of the Earth, we might find a nucleus like zinc 80, which would decay in half a second on Earth by ejecting neutrons. Nuclei with such high ratios of neutrons to protons are only stabilized by the incredible pressures and extreme electron energies in the neutron star. As we leave the outer crust for the inner crust, our nuclei become so neutron-rich that they start to fall apart. We call this neutron drip. Neutrons leak from the nuclei into the ever-narrowing space between them. Now, we don't know exactly how deep this phenomenon begins, but our best calculations suggest that it's close to half a kilometer deep, and we're at least 1 trillion times the density of matter on Earth. We are really relying on our theoretical calculations here. We're beyond the point where we can duplicate these energies and these neutron-rich nuclei in particle accelerators. As the neutron drip intensifies, the space between the nuclei fills with a neutron gas. Meanwhile, the electron gas gets thinner due to the electron capture process. In fact, the neutron gas starts to take over the role of the electrons. Neutrons are also fermions, and so two of them can't occupy the same state. The star is now increasingly supported by neutron degeneracy pressure, but neutrons can get much closer to each other before this degeneracy pressure kicks in, and so much higher densities become possible. Further down, the nuclei themselves start to get fuzzy, as protons are outnumbered by neutrons 5 to 1. A given neutron's wave function is so spread out that it becomes hard to even localize it to being inside a given nucleus. By the time we reach the bottom of the crust, around 1 kilometer deep, densities have reached 100 trillion times that of the Earth. Here, the once distinct nuclei are beginning to touch each other. As we drop beneath the inner crust, things finally start to get properly weird. Welcome to the pasta. Specifically, nuclear pasta. This is perhaps the least known and most freaky state of matter in the universe. When nuclei start to touch, they rearrange, forming exotic shapes. Nuclei have a sort of competition. While neutrons and protons feel a very strong short-range attraction to each other due to the strong nuclear force, the electric repulsion between the remaining protons tries to push them as far away from each other as they can. Down here, there may be 20 neutrons for each proton, so the protons can't really resist the forces reshaping the nuclei. The result is this game of particle tug-and-war. With all this pushing and pulling, we see a complete rearrangement of matter. Nuclei reform radically, forming cylinders containing many millions of protons and neutrons. Nuclear physicists affectionately call this phase of matter spaghetti. At slightly higher densities, this nuclear spaghetti may be squeezed together to form sheets. That's right, nuclear lasagna. And because it's so dense, it's really hard to bend and move this stuff. Nuclear pasta might even be the strongest material in the universe, a quintillion times stronger than steel. The enormous strength of nuclear pasta allows it to resist the insane gravitational forces and so support a sort of jumbled texture, sort of like nuclear pasta mountains buried beneath the star's surface. These could be as tall as 10 centimeters, which doesn't sound like a lot until you remember that every cubic centimeter of nuclear pasta weighs as much as a mountain on Earth. As the neutron star rotates, these buried neutron star mountain ranges get dragged in circles, making a very weak gravitational wave signal. These gravitational waves are much weaker than the signals that we've detected when neutron stars or black holes merge, and so it's much harder to detect them. But instead of being a big splash and a crash, it's a continuous hum at exactly one frequency, twice the frequency of the neutron star's rotation. And gravitational wave astronomers are searching for these signals with LIGO right now, targeting pulsars in our galaxy using their known rotation frequencies. They haven't found anything yet, but they might soon, giving us the first glimpse of the inner workings of neutron stars. By the time we reach the bottom of the pasta layer, just above the neutron star core, all of that matter has been smooshed together into a soup of mostly neutrons and just the occasional proton. The density here is 200 trillion times anything found on Earth. And so we've arrived at the core, where we find the most extreme conditions in the entire modern universe. Here, pairs of spin-half neutrons become connected in a particular way to form what we call Cooper pairs, which actually act as single spin 0 or spin 1 particles. So some of our fermions effectively become bosons, which means that they can do some pretty crazy stuff. In the case of neutrons, they become a superfluid, a frictionless fluid that can do things like sustain vortices with enormous amounts of energy. Some physicists think that the dissipation of these vortices is seen by us as glitches in the frequency in the flashes of pulsars. The rare Cooper pair protons, on the other hand, turn the core into a superconductor, which is probably an essential part of maintaining the neutron star's enormous magnetic field. Approaching the dead center of the neutron star, and even the protons and neutrons start to lose structure and mush together. Now, this is all highly theoretical, but it may be that at these extreme pressures and energies, we find hyperon particles containing strange quarks. Or they might not be bound into particles at all. The protons and neutrons may dissolve completely into a quark-gluon plasma. And we've talked about quark stars before. While these plasmas have been seen in collider experiments on Earth, we're not sure if they exist in neutron stars. The only other time matter existed naturally in conditions like these was within a fraction of a second after the Big Bang. If you're quiet for a second, listen carefully. You might hear the faint booms of thermonuclear storms raging above us on the surface. It seems that our neutron star has started accreting matter from a binary partner star. Its mass is growing, and at some point soon it'll form an inescapable event horizon, and we'll be stuck inside an actual black hole. Escape will become even more impossible than it already is. I think it's time to power up our anti-gravity boosters and leave behind the strangest and most extreme parts in all of space-time.